Welcome to the Sigma Made Simple channel, where my decades of experience is used to explain the principles of Lean Sigma and Six Sigma so you may learn to be more effective in using these tools. This is a walk around video showing the enhanced value stream map, how to fill it in, and its features. We'll go through each tab in the enhanced value stream map and I'll explain how to fill in the yellow boxes and why. You'll notice every sheet in this worksheet has yellow boxes. That's where you'll interact. There are 6 tabs. We'll explain the purpose when we review each one. So the base data tab, we pull that up. Notice that it's going to have project specific information. And in this case, it's going to be a high complexity product. I have actually 96 connectors on one side and nothing on the other. But go through this really quickly. So I filled this in to save us some time. So, but on the base data tab, you're going to see yellow cells. These cells are what you're going to interact with. If any data is not available in this tab, don't worry about it. I'm going to tell you what's required, and you can fill in the rest later. But I suggest you put something in everywhere. So from the project charter, you will get the champion. And then let me make this a little bit bigger. From the project charter, you're going to get the champion, stakeholder. Again, the champion is going to be one person that everybody reports to. As you go up the chain of command. Stakeholder could be one person or could be a group, could be more than one person, could also be the champion. You get the leader of the team from there. And then you'll put the date. And the date is the date that you start this enhanced value stream map. So whatever today is when you start filling this out, that's what you'll put in there. So in this case, select a product. It's going to be the H1HD project, HO product. And then our line or focus area is going to be line 4 of 10, shift 1 of 2. Then we're going to go down and fill out the rest of these things. I'm not going to go into a lot of detail. Let me just zoom in a little bit here. You're going to do the product volume. You can read this to figure out what that is. There's also an earlier video. It's linked in the description that explains all of these things. Product visibility, here it's going to be high, as well as product volume is going to be high. Your product variation is going to be low. The product complexity is low. I'm sorry, product complexity is high. I'll switch that. Then our data trend is constant, and that's basically flat, no trend going up or down. Oops, I want to zoom out a little bit. Then our data frequency, in this case it was multi. Like I said, there's a video linked in the description that tells you how to determine these things, but multi-frequency is basically, if you look at this little graph here, you can see there's 2 populations. The orange is higher than the blue dots, and that's by shift. There could be any kinds of things with multi-frequency. Previous video linked in the description is going to show you how to determine that. Then your output. Your output is something that you're going to be required to have. It should be a number rounded to the nearest whole number for the historical output or the focus line and area. It should be verified. There's a previous video linked in the description telling you how to verify this. You could leave this blank, I suppose, but it's best to have something in there and then to verify it. If you don't have any historical data, then you should collect data on a line that's fully loaded with people, fully loaded with materials, and fully loaded with work for anywhere between a minimum of 10 days and ideally 25 working days with no issues. And that's going to give you some good data to look at. If you have some data that you're suspect, previous video linked in the description is going to tell you how to clean it up. So you are required to have the total daily working hours. And that's right below the output. So in here, it's got 17 hours because there's 2 shifts, each having an 8.5-hour workday. Okay, that's 17 hours. You are also required to have the daily working hours. And this should be pretty easy to figure out. Here, it's 15 hours because each shift has a half-hour break and two 15-minute breaks. And then, so that puts us, basically, we're burning up 2 hours of our work total daily hours, um, an hour per shift. So it puts it at 15. If you do have a scheduled meeting, or maybe there's 10 minutes of cleanup every day, you can add that in there as well. Anything that's scheduled for every day where the operators are not actually working, you would take that time off as well. Last is the labor rate. I got 3250 in here. This should come from finance. It's not required, but it's highly suggested that you do this because it's going to be doing some calculations, looking at costing. Usually it's direct and fringe, but it might be a little different. So talk to your finance department and find out what kind of a number you need to put in there. All the savings in the spreadsheet assume that the lines will be fully loaded with work, materials, and personnel in the future. And that's what we're working towards. We'll discuss the areas below in more detail later, but they are just a result of the current tab and the proposed tab calculations, and then what you would have, what the change is. So back to the next slide. And that's the current tab. And the current tab is the way the line works today. I'm going to bring that up. I'm going to zoom this in just a little bit to make it a little easier. Now, the purpose of the current tab is to identify the bottlenecks. It will measure your output within 10% at least, and hopefully within 5%. I'm going to go through the prep workstation in column C. I'm sorry, let's go over here. Here we are. Column C, we're going to review the prep workstation. Just going to go right down the line here. So the name is prep. And then if you look at the next line, it's the units. The units here are 96 for prep. This is the batch size the workstation works on for your cycle time. So in this case, the operator will prep one cable having 96 fibers that require a connector. Some may think this isn't necessary, but it helps you in understanding the processes as well as why it takes so much longer to turn an order around in production. We'll get to that later. But it is important to capture it so you better understand it. Below that is the cycle time for that batch or those number of units. In this case, the base process is fixing a single connector on a single fiber. So be sure to collect the total labor time for your cycle time. So in this case, what they did was they took us time studies of uh, prepping a cable, and they did like 20, collected 20 bits of data, and then took the average standard deviation and put the average in here. In this case, the total is about 7,972 seconds or 2.2 hours. When collecting the cycle time, be sure that you start when the time when the person grabs the first cable or connector and ends when they grab the next cable or connector. So if it takes 2.2 hours, just put that time in there, the 79.72. Don't worry if you've got two operators in there. The enhanced value stream map is going to take that into account when it looks at the total costs. Don't worry about the number of workstations just yet. Just take the time down. So even though it might have taken 2.2 hours of time to do the job, we do know that's 4.4 hours of labor. The enhanced value stream map will make that adjustment. Just put 2.2 or 79.72. Downtime is any time that is scheduled for that workstation other than breaks and lunches for the operator. So right here, I don't have anything in downtime for this right now, but let's say every 2 hours you would spend 10 minutes calibrating a piece of equipment. That would be 5 minutes per hour, and you would put 300 seconds in this cell. So downtime is the seconds of downtime per hour. So you have to take the total downtime and then divide it into how many is in each hour. First pass below that is your workstation count. the number of workstations working on that same process. You're going to notice here for prep, we've only got one workstation. But if you look over here at pot, we have two workstations. And there's two people working on those two workstations. Um, so that's, don't worry about, don't worry if you, don't worry about any adjustments that need to be made. The enhanced value stream map is going to make an adjustment on your cycle time based on whatever the number of workstations are. And then next is your total operators. That's the total number of operators per workstation. So here we've got two operators on one workstation. And for pot, we've got two operators for two workstations. Just put the number of operators in there per workstation. Then your first pass yield. It's the percentage of product that's conforming, either by inspection result or not being damaged during the process. And the next is the value added or non-value added is whether the process is adding value or not. Typically, when you make a material change to the process to the product, it's considered value added, something that you can't do without. Inspections are non-value added. There's a third condition, which is non-value added required. That might be something like an inspection point that you feel you don't need to do, but the customer is going to require it. So in row 14, you're going to look over here at this non-working WIP, and that's the amount of product sitting and waiting in non-working WIP for that next workstation, which would be prep in this case. So there's 12 connectors sitting, or 12 cables sitting in there waiting for the prep operator to do something with that. So after you fill this in, and you haven't put anything else in, but just with this data alone is what I was told to capture for my value stream map when I was trained. And what's the not so good about that is if you look at your base data tab and you look at your output 360, let's say you verified it and 360 is the average or the mean for your output. But then you come down here, oops, and what you see is your output on the VSM for the current is 429, and that's way higher. So it's not usable. We have to be within 10%. And so now we have to go back and look at why we're not even close to our actual output. So just to reiterate, our output is supposed to be 360. The VSM says it's 429. It's 19% higher than the actual output. So we must be within 10% to make accurate predictions. So we must fill in the rework questions. Note that you may have thought prep was a bottleneck. I'm going to go back over here. People who are new may think, well, there's my bottleneck. It's got the most time, but they're doing 96 units. So what if we remove prep? Let's just take this out for a second and see what happens. And then it looks at pot. So it may not always be obvious where your bottleneck is, especially in the beginning. But if we do remove pot, so we've removed prep and now it says pot. Okay, well, let's remove pot. And then polish appears to be the bottleneck, which probably, may or may not be. But then again, you always got to look at the number of units being detected or batch size being processed. But polish may not be the bottleneck either. So what we're going to do is we're going to fill in our rework issues, and then the spreadsheet is going to take into account all of the factors to tell us where our bottleneck is. So we're going to go to the next tab, but remember that the current tab is the way that the line works today. It identifies bottlenecks, and then you can measure your output within 10%. Should be able to. I'm going to go to the rework sample. Now I've put some numbers in here already. I've filled these rework data in so you can see the impact. On line 11, put the workstation that any non-conforming product goes back to. And that's for each workstation. So in here, we're just going to put a 1, even though we've got 100% yield. I put a 1 here. And we're going to go to where it's like end face. Um, it's got an 85% yield, and it goes back to 3. 3 is polish, so this goes back to polish. And for geometry, it's a 3. Has 90% yield, so 10% of the product needs to go back to polish. And here, crimp, 99% first pass yield. 1% of the product needs to go back to workstation 1, which is prep. And then we look at loss. 1% of the product goes back to prep. So if there's any online rework anywhere on the line, the whole row 12 should be online. For wherever they go back to, that workstation needs to be online, and wherever they're being sent from needs to be online. Now, in some cases, you might decide that you're going to that there is some offline. So let's say that we do have something that's offline. I want you to look at the numbers in row 16, right around here. I'm going to take this, actually, well, let's take geometry. Let's take geometry offline. And I want you to look at the numbers in the gray boxes, the 106.4, and then to the right, the 35.7. And I want you to look at the polish. Once you go offline, they all change because now that product is no longer, those non-conforming connectors are no longer being processed. I'm going to put it back to online because I don't want to mess things up. So lastly, line 13, for each workstation, put down what it would cost if you did send rework back to this workstation. And you don't include the labor, just include the material costs. And for example, for prep, it's $3.50. If something comes back here, it costs us an additional $3.50. For pot, it's an additional $1.20 because we're only putting in what that workstation has. Same with polish, it's $3.13. All of these things that we're doing here, turn the lights on, and what is usually your hidden factory is typically where a lot of waste goes unnoticed for years and years. Note that the data is usable on the base data tab. I'm going to come back here because we've already recalculated row 16. This is your workstation factor, and it's basically what your actual cycle time is per that group or per connector, per single connector, based on the number of workstations, the number of units, your cycle time, the number of operators, everything, how much rework gets sent back there. So you'll notice that it's 1356 divided by 12. It's like 100 and your cycle time would be like 100 and some seconds, 115 seconds per connector. But because of all the rework being sent back, your workstation factor is 143.5. So that's what you need to look at when you're looking at your bottleneck. I'm going to go back over here to base data. We're going to slide down. And now the VSM result is usable. It says the VSM output is 368 and the output is 360. That's very close. And that tells us that we can use this VSM for predicting costs and predicting change. So the proposed tab is the way that we predict the line will work. The proposed tab should begin identical to the current tab. And I'm just going to take the current tab and I'm going to copy all of this. By the way, those the non-working whip on row 14, that's the only thing you should not change between the current tab and the proposed tab because they are used for some calculations, and if you change those, you could artificially change your output without really having any effect. I want to show you though the current tab. OCE is 43.4, cost per labor or per unit is 1504, 368. And if you look at the proposed tab, it's basically identical. So what it's telling us is that, yeah, we've copied these over and we're going to start with them being the same right off the bat. So now you can go to the proposed tab and start making changes and see what kind of an impact those changes are going to have. Um, it's very important um, that you start with both of these identical and that you do not, again, change the non-working whip. So when you start making changes to the performing tab, over time, you're going to notice that there's a law of diminishing return where you maybe you're not going to save as much money. That's another nice thing about the value stream map is it's going to tell you whether or not it's really worth working on something and not only what you could do, but also what you need to do to achieve your goals. So let's say that you want to know how much you'll save if you increase the first pass yield at end face to 90%. The base data tab shows a savings of about, well, let's make this change. We're going to go to 90% for in face. Now we can go to the base data tab and it says that, yes, we're going to improve things. Um, our performance and quality. Did you notice that once you increase your first pass yield that you're affecting performance and quality? You're getting a double bump there and it's going to go up to 47.3%. Your OCE is going to go up. If you scroll down, it's going to tell you on line 39 that you're going to save $70,722 per year just for increasing that to 90%. Let's go back and look at, let's put this back to 85% and let's say what if we increased geometry to 95%. Look at our base data. It's the same. We're going to have the same impact. And we might want to combine these because in this particular case, we might find that polish is a key process input variable for in-face and geometry. So if we did combine these, let's say we're going to go to 90% here, and we're going to shoot for 95% of geometry. Oh, now it's $147,000 per line per year. So if you got 10 lines, that could be $1.5 million that you would spend to upgrade 10 lines to increase your geometry from 90% to 95% and in face from 85% to 90%. I'm going to put these back real quick just to make, actually, I'm not going to put them back. I'm going to leave them right where they're at, 90%. So you can do these types of things to kind of figure out what you could do for Six Sigma projects. You can also look at rebalancing the lines, taking things from one area to another. Let's say you have an improvement idea to take some work from polish to pot. Okay, and it's really simple. But let's say that management or somebody else or another team says we want to wait to do this, or we're going to go with automation. So don't work on that because we're going to do automation. Uh, Well, the problem here is that there are no guarantees for any change. And when you're faced with something like this, where you can make an impact, a small impact really quickly, but somebody wants you to wait. I recall a few of the basic principles of Lean Sigma and Six Sigma. The first one is never put off better for perfection. If you can do something today, do it, because what you want to do in the future may not be may not work out. Another one is plan for what is today rather than what may be tomorrow. These ideas are going to keep you moving. And what you might find is that if you make enough of these small changes, you may negate the need for automation or for these bigger projects, or you may redefine how that automation needs to perform so that your functional requirements change and make that automation more focused and better. And that's typically what ends up happening. So once you decide on Six Sigma projects by playing with the numbers here and populating the EIC tool and doing the initial project charter, you may decide to combine them. Like in this case, you may find that the KPIV for in-face and geometry is the same process at polish. So you may combine them in one project, but never combine projects unless they share the same KPIV. Complete the project and make one change at a time based on the project results. If you decide to keep them separate, implement them separately. So if they're separate projects, implement the solutions to each project separately. Make sure that they're having the desired effect. And if they're in one project, then you can implement whatever the result of that project is. So let's go over to the questions tab. Basically, the questions tab is a list of questions you'd ask operators in the focus area. This tab is a refresher on the questions you'd ask. Um, so you can add things to it. They're not protected. You may have noticed you're kind of limited in a lot of ways on the spreadsheets, but there's no password for these spreadsheets. You can just hit unprotect anytime you want. And then let's go to the Changes tab. And the Changes tab is basically um, the list of changes you made between the current and proposed tab. In this case, we said we're going to we increased the first pass yield at in-phase from 85 to 90%, geometry from 90 to 95%. We, um, we also affected the OCE performance and quality, which was nice. Now, you would normally only have one thing in here, but some people, they like to keep a log of all the changes. So it's like a living document where once they finish the proposed, they copy that into the current and they make a new revision and then they go to the next one and then they just keep copying the current over to proposed, the proposed when it's implemented back to current, and then they um, keep making changes. And you can just keep adding those up if you want, but normally you'd only have one document and then you'd only have one change. So now we're going to talk about turn time. This is a very complicated tab, as it is a comparison of your turn time between the current and proposed tabs. Your turn time is basically your first off time. I'm going to explain this better in a little bit better detail. Um, 1 minus your quantity times your rate. Let's pull that back up. So the turn time tab is a comparison, like I said, between your current and proposed. This tab gives you an idea how long it will take you to put specific production order through manufacturing. It is best at looking at the difference between the current and proposed tabs. It may not necessarily be accurate since there are so many variables to consider, but especially the way that people run lines as opposed to something like this, which is perfection every single time. So things might be a little bit different because of that. But you put the working days in to deliver your order in cell D10. And in this case, we're going to have 10. And then cell D11 has the units needed in that number of days. And in here, we're going to start with 20. And then put the number of connectors on N1 and N2 and F12 and AA12. In this case, we're going to have 96 connectors on one side. You can leave this blank. Look at the top of the page. Cells B1 to D4 will give you an idea on what you may expect. So what it says is your current turn time and working days is 7. Your proposed working time is 6.5. So you will, after you implement the proposed, you can deliver that product in half day, less time. As an engineer, you should always know 3 things about your line. One is your takt time. Your takt time is the time it takes for you to satisfy the customer's order. So takt time is what you want to achieve at minimum or beat. Some people get that mixed up with cycle time, but or your rate, but that's not the case. Takt time is based on what the customer needs are and what your rate needs to be in order to satisfy that need. So in cell C1, it's 5.8. So you need you need to have a rate of product coming out the line every 5.8 hours to make the customer happy in this case. The rate in cell D13 for current and D50 for proposed is your actual rate. So if we look at your rate here, It's 3.83, which is less than 5.8. So you're in good shape. And if you look down here at the proposed, it's a 3.53, which is you're in good shape. So you should know takt time, you should know your rate, and you should know your first off. And your first off is how long it takes. It's a number of hours it takes to get the first one off the line after you start your order. In this case, for current, it's 30.2 hours. So uh, after 30.2 hours, your first unit comes off the line. Then every 3.83 hours, you get another one unit off the line. That's for current. For proposed, it's 28.8 hours. You get the first one off the line. And then your rate is 3.53 hours. You get an additional unit off the line. You can also look at the number of units delivered. So for 14 units delivered, you can do 31 units in that 10 working days. You come down to proposed, and your units, you can do 34 units. Now, what if we had 35? What if we needed 35 units instead of 20? Well, that's not so good. So you can look up here your current turn time. Your current line is zero point 0.9 days over the days needed to deliver. And also, you're over on there as well. What if we did 30? And you're okay. So you can kind of play with this and kind of figure out. It's 31 units here. It's 34 units here. And so if I make this 33, and you can see your proposed can make it, but your current cannot. So you can use this to kind of play with your proposed to see what you can, if you can meet the customer's demand or not. And you can also use it to see which ones, how your turn time is being affected. Again, your turn time is the number of days it takes to the uh, turn the order around, and you can compare that to what your customer's demand is. So the enhanced value stream map has many automated features to help you avoid identifying the wrong bottleneck and wasting your time. It can show you major impacts, what may take time, uh, but it can also show you the smaller impacts, and it can be done quickly while giving you a good idea on what your impact would be. You can play with the numbers to see how much you can spend to make improvements, and these improvements will impact your ability to reduce your lead time and to your customer. Remember earlier, we predicted that we're going to spend 70,000 or save $70,000 if we improve geometry. Well, that would be used in your project charter. Spend no more than $70,000 to save $70,000. I always use a 1 year payback. You can talk to finance. Maybe they'll want you to use a 3 year payback, so then you could spend $210,000 instead of 70. But if you found this video useful, like it, subscribe to the channel, and share it with anyone else who may find it useful. If you didn't find this video useful, then subscribe in the hope that an upcoming video will be. Eventually, we're going to go through projects such as Lean Sigma, Six Sigma, and the tools needed to support them. But remember, never put off better for perfection, and plan for what is today rather than what may be tomorrow. Until next week, keep your data clean and your mind open.